So we talked about finding critical points, and the critical points provided us candidates for local extrema, local maxima, and local minima. Well, how do we classify the critical points? How do we know whether they're local maxima, local minima, or neither of those? How about maybe a saddle point? For that, we're going to use the second derivative test. And in order to carry out the second derivative test on a critical point, we're going to need something called the discriminant. And the discriminant of a function of two variables is given by the determinant of the Hessian matrix. The Hessian matrix is composed of the second derivatives of a function of two variables. Taking the determinant of the Hessian matrix, we arrive at this expression. And when this holds true, and we know it holds true by the theorem of Clairaut, so if it satisfies the hypothesis of that theorem, then we could write the discriminant in this way. And we'll only be dealing with situations in this section where the discriminant is expressed this way, and so you don't have to worry about that. So what's the second derivative test? Suppose the second partial derivatives of f are continuous throughout open disk centered about the point AB. Moreover, suppose that that point AB is a critical point due to both of its partial derivatives simultaneously being 0 at that point. And let this be the discriminant that we saw above and here. Then we have these four scenarios to consider. For the discriminant being positive at that point, and notice here that the discriminant is a function of two variables. So plugging in the critical point, if you get that the discriminant is positive, there's two situations. If also the second partial derivative with respect to x at the point AB is strictly negative, then f has a local max at AB. If the discriminant is positive at the critical point and the second partial derivative with respect to x is strictly positive, then f has a local min. Okay, so these first two situations are when the discriminant are positive. So when the discriminant is strictly positive, we then look at the second partial derivative with respect to x, and then we reach our conclusion. What about if the discriminant is strictly negative? Then f has a saddle point at the point AB. Okay, no need to check the second partial derivative at that point. When the discriminant's negative, it's a saddle point. And when the discriminant is computed to be 0 at the critical point, then the test is inconclusive. Something to note here is that instead of the second partial derivative with respect to x, we may use the second partial derivative with respect to y also. So let's use the second derivative test, and let's take a look at this function. Now we found the critical points of this function. Here we had 5 critical points. We looked at the partial derivative, set them equal to 0, and found these 5 critical points. At these points, both partial derivatives are 0. But we need the discriminant in order to carry out the second derivative test. And so we take the second derivatives. We have that for f double x, and we have for fxy this, and fyy that. Okay. Computing the discriminant, we get this expression, and we could write it like this. Okay, so this is the discriminant as promised. It's a function of two variables. Now, what do we plug into that function of two variables? We plug in the critical points. So I'll take the first critical point here, 0, 0, plug it in, and I get minus 36. Now, I go up, I say, okay, the discriminant's negative. All right, that's situation 3 there. So we have a saddle point at 0, 0. Now, I could do this to the different points. So plugging in 2, 0, we get minus 36. That means that the critical point at 2, 0 is also a saddle point. Plugging in this critical point into the discriminant, we get D is 9, which means it's strictly positive. And what does that mean? Well, let's go up. Strictly positive. Okay, we're in the scenario of 1 or 2. And so I have to look at the next thing now, the second partial derivative with respect to x. If it's negative, we have a local max. If it's strictly positive, we have a local min. So let's see in this situation, positive and strictly negative, so we have a local max. Plugging in the rest of the points, we see that the rest are saddle points. Again, here is the function that we were looking at, and we classified its critical points. And as you could see, there's one local max, that red dot there, at the point 1 minus 3 halves. And the rest of these are saddle points. You can see it looks like saddles at the 4 corners, with one local max at the top of that peak. So let's take a look at another example. We're going to apply the second derivative test to the function that you see there. Let's look for the critical points. Taking the partial derivative with respect to x, it's 8x cubed, setting that equal to 0. Well, that implies x equals 0. The line x equals 0 is where this function has a partial derivative with respect to x being equal to 0. Doing the same thing with y, we get y equals 0, so we have to satisfy both of these simultaneously. These two lines intersect at the origin, and so 0, 0 is a critical point. So let's now find the discriminant. Okay, to do that, we're going to compute the second partial derivatives, and our discriminant looks like this. Okay, plugging in the point 0, 0, our critical point that we found, we get that the discriminant is 0. And what that means is that this test is inconclusive. Now, just because the test is inconclusive doesn't mean that you can't have a local max, local min at that point. Okay? You could have any of these circumstances, the local max, local min, or even a saddle point. And we can take a look at this function. And here's the function that we were looking at. F is equal to 2x to the 4th plus y to the 4th. And you could see here at the origin, there is in fact a local min, but the second derivative test was inconclusive. Okay? And now there are means to actually go from an inconclusive result of the second derivative test and apply more derivatives, but we'll just settle at saying that the second derivative test is inconclusive here. Although, in fact, 0, 0 is a point where the function has a local min there. And here is a second function of two variables that has a critical point at the origin, 0, 0. But it turns out that the second derivative test will be inconclusive for this, although at the origin is in fact a saddle point. So the second derivative test could not pick that up.